welcome to virtual open hours at the Environmental Education Center. Today we are going to be talking all about geology. So I'm sure when you think of geology, you're probably thinking of rocks and minerals, and it's true that scientists, geologists do study rocks and minerals, but geologists study a lot more than just that. Geology is the study of basically how the earth is made, any of the materials that are made up in the earth. So geologists will also study things like fossils and soils and landscapes, how things like mountains form, all of this different stuff. So today we are going to be thinking a little bit like a rock scientist. Now the specific geology term for a rock scientist is a petrologist. So we're going to be studying some rocks and then doing some fun activities together today. Now, a petrologist, when they're studying rocks, they would want to do a couple things. They would want to observe the rocks for their rock properties, checking out things like what the color, the shape, the size, the texture of the rocks are, and then they would want to identify or name them. So there's a lot of different names that different rocks have, and there are different categories that we can put them into as well. So we're going to go over some of these different words that we use to describe different types of rocks. But first I want to start off by mentioning what's the difference between a rock and a mineral. They are different. Rocks are made up of many different types of minerals. So I actually have a couple minerals here to show you. Very diverse sets of minerals. This one is quartz. It's the most common mineral. Then we have some jade. I actually have a jade necklace on today. And this is a really cool shiny type of mineral called mica. So all of these and many more minerals are found in rock. So you can kind of think of a rock as like a salad. So in a salad, lettuce, cucumbers, tomato. Each of those items that make up the salad are your minerals. So you have a lot of different minerals in a single rock. And the first rock I want to show you is this really cool one that has a lot of layers in it. Take a look at all those lines. This rock belongs to a group called Sedimentary Rocks. Sedimentary rocks, yeah. There are some things that all sedimentary rocks will have in common, or most sedimentary rocks will have in common. A lot of times, sedimentary rocks will have visible layering. That's why you see all these lines on the rock. Now, the way a sedimentary rock forms is at the surface of the Earth's crust, the outer layer, and tiny pieces of sand and other sediments are going to be moving around and then settling and compacting together. And they will form this sedimentary rock. So over long periods of time, you'll have different sediments getting pushed on top. And you can kind of figure out a little bit about how long or how old this rock is based on the amount of layers that it has in it, that it's developed over time. So we have another layered rock that's called sandstone that we're going to take a closer look at underneath the microscope for a second here, so you can really see the layers in this rock and also just get the chance to look at some of these rocks up a little bit closer. So you can kind of tell there's some color differences in between those lines, those layers in there. You can see some prominent lines going through there. So those are all different minerals. Those different colors are because there's different minerals in the rocks. And one of my favorite things about sedimentary rocks, sandstone is just one type of sedimentary rock. There are a lot of different types of sedimentary rocks, and there's also a lot of different types of sandstone. For example, I have one here. This is another type of sandstone. Looks pretty different than the one underneath the microscope. That's because this type of sandstone is called bluestone. So bluestone is one type of sandstone rock. And you'll notice the one I have here doesn't really have any layers. But what I do love about sandstones is if you look at them with underneath a magnifying glass, or in our case a microscope, we're zooming in all the way to maximum zoom, maximum magnification, so that we can see all of those individual grains, those individual sediments. So each of those little dots, the darker ones and the lighter ones, different minerals that are in there. Yeah. So probably some of those lighter colored ones, those white ones, possibly are quartz or some other type of light colored mineral. So you can really kind of see those grains inside the sedimentary rocks. And that's one easy way to tell. If you look at a rock and it looks very grainy, that's a sure sign that you're looking at a sedimentary rock. So even if it doesn't have layers, you can still kind of figure out whether you're looking at a sedimentary rock or not. But there's two other types of rocks that we're going to look at. Oh, actually, I have a few more sedimentary rocks to show you. So as I mentioned, the layers will form on some of these sedimentary rocks. And the reason why those layers are forming is because the wind and the water is pushing things around. So just like wind and water can push things together, I actually have a really cool conglomerate rock here to show you. Or actually, I think this one would be called a breccia rock because of the shape of it. So sometimes wind and air can push things together. And in this case, it can create a rock made out of several different rocks. Weathering and erosion are the words that we use to explain when things get broken apart and pushed around. When a rock gets broken up into pieces, or maybe just like a little bit of a crack forms inside a sedimentary rock, you get something really cool that I bet some of you might have seen before. We got some to put underneath the microscope too. These are geodes. So geodes are crystalline structures that can form in the crevices of rocks, and as soon as water starts to percolate in there, it will react with some of the minerals and the elements that are in this rock, and will form these really beautiful structures in there. So geodes most often found in sedimentary rocks, because again, sedimentary rocks found on the crust outer surface, that's where they're formed, and they're experiencing a lot of changes due to the weather, right? Due to all of the wind and rain and storms that can change these rocks over time. Weathering and erosion. All right, now the last thing to know about sedimentary rocks, and probably the most exciting thing, is that they have fossils. So here's an example of a fossil. We have some ferns fossilized in this rock. You can also have really big casts of fossils. So here's a good comparison. We have on the left side, we have a shell fossil that is kind of like a print left behind on the rock. Then what I have here, this is also a shell fossil. This is from an ammonite, and what you'll see is it kind of looks 3D. So what happened was the shell or another animal or plant part gets stuck in between those layers. Think about all of those layers we mentioned. They get stuck in between the layers, they get compacted together, and over time, the organism's body will start to decay and break away, but it'll leave behind a print. And in the case of this one, what we call it the cast fossil, somehow the new sediments are going to kind of fill in that gap that's formed in the rock. So kind of just like when you make a mold of something, you have a mold, you push something into it, and then you're able to pull it out and it looks just like it. So that's pretty cool. Now we have fossils in the park. Here's an example of one of the common fossils we see in the rocks in Brooklyn Bridge Park. These are from limestone rocks. You can find fossils in a couple different types of rocks, but limestone is a rock that really preserves the prints very well. So we most often find fossils in limestone rocks. So we had, the first print was from a brachiopod. That's a animal that is it's a shelled animal. They're not really around much anymore, but they were pretty prevalent in the waterways here millions of years ago. And then we also have, this one's called a crinoid. Now it might not look much to you, but it's actually the cross section of a stem of an animal that is sometimes referred to as the sea lily. They still exist in some parts of the world, deep in the ocean. And the sea lily had these beautiful stalks that they affix themselves to on the ground. So you can see we're moving around the fossil to show you that that print is on both sides. So that's because it kind of, the stem kind of went through an area of the rock. When you break a rock in half and you have that crinoid fossil in there, you're just going to see that circle cross section. So that's the crinoid. Now, if you think you have a limestone rock, but you're not sure, there's actually a fun way that you can test at home whether you have limestone or another rock that is sedimentary. A lot of sedimentary rocks will have calcium carbonate in it. Now, if you think of animals with shells, they also have calcium carbonate in their shell. Calcium carbonate is just another form of calcite. Calcite is another mineral. So think about like salt, calcium, salt. They all have this. Initial atom in them. So we're going to do something called the acid test or the fizz test. We're going to put some vinegar on our rock. If it fizzes, that is a sign that there is calcite in this rock, that there is calcium carbonate. Let's see. I see some bubbles there. Yeah, there's a lot of bubbles. So when you do this test, it helps you kind of be able to figure out some of the elements and the minerals that are in your rock. And with that, it can make it a little bit easier for you to distinguish the specific type of rock you have. Excellent. Because, you know, this rock is kind of gray, but there's a lot of gray and black rocks out there. So you got to rely on more than just color when trying to identify rocks. So fizz test, great way to narrow down your results. And look at that. Those bubbles are still forming. What's happening is there's a reaction forming with the calcite and the calcium, and basically there is carbon dioxide that is being released. That's what those bubbles are. Pretty neat. Now, not all rocks can do this. There's another rock I have here, also a sedimentary rock. It's called shale. Pretty common. You've probably seen shale before. Pretty soft to the touch. I'm going to pass it over to my friends here, and we're going to put this one underneath the microscope and do the fizz test and see what happens this time. This is also a sedimentary rock, but will it fizz is the question. All right. Not seeing, there's some tiny bubbles, but not very much. So my suspicion is this rock probably was sitting next to or kind of mixed in with some of the other sediments that do react with vinegar, but the rock itself doesn't really seem to be bubbling. So we know that it doesn't have calcite in it. But what's interesting about shale is, do you see all those lines? Those are scratch marks. So another test besides the fizz test that scientists will do when they're studying rocks is they will test the streak, or they will do what is called a scratch test. And if a rock is able to be scratched, or it is able to scratch something else, like glass, you can assign it a number based on its hardness. So we'll go ahead and try to scratch the shale right now so you can see. You can actually scratch it with your fingernail. Same thing will happen if you were to scratch chalk. Chalk is a sedimentary rock, believe it or not. So this is a very, very soft rock, and you can do this test with all different types of rocks and see which ones you can scratch and which ones you can't scratch. Okay, so we're going to move on to our next set of rocks. If a sedimentary rock were to get pushed deep down into the earth, you would eventually get close to the mantle. The outer layer is called the crust, and then you have the mantle and the inner and outer core. Mantle, very, very warm down there. So as rocks get pushed deeper into the crust and get closer to the mantle, they experience a lot of heat and pressure. So those rocks that had those beautiful straight lines in them, they might start to look like this. So a lot more bending and folding, kind of mixture of different light and dark colors. We have a rock that is a very common metamorphic rock. That's what we use to describe these rocks undergoing heat and pressure. Metamorphic, think of the word metamorphosis, it means to change. So here's a cool rock. This is called Gneiss. It's spelled with a G, but it's said like the word nice. Like Gneiss is a pretty nice looking rock, right? So what you can see here is, yeah, we see some light and dark banding, but those aren't really nice straight lines. They kind of intersect each other. I'm also noticing that this rock has a lot of shimmer to it or sparkle to it. And that's because rocks that are metamorphic usually have a lot of luster. There's another rock that is a metamorphic rock that's pretty common here in New York City. It's called schist. Manhattan schist is the specific variety that we get here in Brooklyn Bridge Park. In all of New York City, not just Brooklyn Bridge Park. The bedrock, deep underground, is mostly made up of schist. So what you're looking at now on the screen, that's schist, yeah. So all of those very sparkly, that sparkle coloration, that luster, is actually largely due to that mineral I showed you in the beginning, this mica. There's different types of mica. Some of them are lighter variations, some of them are darker variations, and that mica is one contributing factor to why these rocks have so much luster and shine to them. Now, I have one more metamorphic rock that I'm going to show you just very quickly, and we'll actually compare it to the shale rock. So I'm going to grab my shale rock back for a second and show you this one. This is not the shale. This is something different. Here's the shale with our fizz test, right? So shale, slate. This one's called slate. So what happens is when the shale gets pushed down underground and compacted, it kind of metamorphosizes into this totally new rock, much harder, heavier, called slate. So that's just one example of how rocks can transform from one rock to another. We call that the rock cycle, when one rock kind of gets changed and becomes a little bit different than it once was. So there's actually one last group of rocks that's a part of our rock cycle, and that is the igneous rocks. Now, the most important thing to remember about igneous rocks is the way that they're formed. They're the most interesting forming rocks, in my opinion, and that's because they form, it's not really about how deep they form, but what they formed from. Igneous rocks are going to form from magma and lava. That's right, so we're thinking about volcanoes. So magma is what we call molten rock, melted rock, that is deep down close to the mantle. And lava is what comes out of the volcano. So when it's in the ground, it's magma. When it shoots out of the volcano, we call it lava. And there's two different types of igneous rocks because some of them form from the magma and some of them form from the lava. So the one we're looking at right now on the screen underneath the microscope is a very common one that you've all probably seen before. It's called granite rock. Now, some of the most common rock properties with igneous rocks are that they can have a little bit of a polka-dotted appearance. So you can kind of see, especially in the one I'm holding up right here, you can see a lot of dots there, little black dots. Now, we flipped over the granite that's underneath the microscope because it looks a bit different on the other side. You've probably heard of granite before because it's in our countertops. Sometimes it's in our floors, our tables. People use rocks in a variety of different ways, and granite for a very long time has been used to build things in our houses. So when we polish rocks, they look a lot different. So this is the polished side of the granite. Let's quickly flip back over to the other side to do a comparison. That's the natural side, and then we'll flip it back again to the polished side. And it's pretty neat to look at this polished side, especially underneath the microscope. And you'll notice it looks a lot different than our sedimentary rocks when we zoomed in, right? The sedimentary rocks, you could really see those very specific separate dots, separate sediments. Through this transformation or formation from magma, we get a different appearance, a different look in these rocks. But you can still tell that there's different minerals in there. The lighter ones, the reddish ones, those are called feldspar. And then I have a couple more rocks that I'm going to show you that are formed not from magma inside the earth, but from lava when it cools. Now, if you think about an exploding volcano and how hot lava is, it is very, very, very hot. So different than a granite rock, which slowly cools very slowly over time. The rocks that form from outside lava are going to cool very quickly. They're cooling so fast that they start to have all of these air bubbles forming in them. Now, we're looking now at a rock called pumice. You see all of those little circles in there? So I got a bigger sample here. You can really see all of those spots. We call this a porous rock. Porous. So water would be able to seep into this rock. What's also interesting about pumice, if you ever find yourself with a piece of pumice or what you think might be pumice, you can double check by putting your pumice in water and seeing what happens. Because it is a very light rock, while these holes bubble where the air was escaping, make it a very light rock. Even when it's really big, it's much lighter than some of my other smaller rocks I have here. And the pumice will be able to float on the water, actually, because it is so light. So if you have a rock and you try to float it, and it does float, you know you have pumice. Excellent. Now there's another rock similar to pumice that's called scoria. So different color, which means probably some different minerals in it. Actually, there's two different types of scoria here. So we got a red variety and a black variety. And yeah, these ones, the holes might not be as big in this rock, but if we zoom in, you'll be able to still see that there are some tiny holes. Yeah. Excellent. So air bubbles, one main feature of rocks that come out of the lava, but there's also a very cool rock that I have to show you in front of me, and this rock is called Obsidian. Obsidian's a very shiny rock. So, got that one there. Yeah, Obsidian. Another cool rock that forms from magma. All right, so we've talked about all these different types of rocks, their names, their groupings, but I bet we're kind of wondering a little more about one of our favorite geology concepts, the volcanoes. We know that rocks can form from volcanoes, but how do rocks form to begin with? It has something to do with plate tectonics. So in order to understand plate tectonics and how a volcano forms, we're going to have to learn a little bit more about what a plate is. So my friend Marley's going to come on. She's going to tell us more about that.
Hi everybody, my name is Marley, and like Christina said, we're going to be talking about plate tectonics. So the first thing we're going to talk about is Christina used this model of the Earth, and so on the outside where we live, that's called the crust. It's a very thin layer, and on the outside where we live, we have plates that are broken up into smaller parts of the crust, kind of like a puzzle piece. Now, over time, the land has moved where the land and the oceans have been A long, long time ago, billions of years ago, all of the land was in one supercontinent called Pangaea. And over time, the land has moved to be in different places. Now, that happened because on the crust, with all those different plates that we call plate tectonics, they float on the mantle where it's very liquid. And so it's very easy for the crust to move very slowly. They move just about as much as your fingernail grows in a year. Can you imagine the land moving that little? And so over billions of years, we can see how the land has changed. So plate tectonics are a big role in the rock cycle and how we get new rocks and how old rocks are transformed back into new ones. So today we're going to be doing some modeling with the different types of plate tectonic boundaries. So for the boundaries, we are going to be talking about how they come together. They all fit together kind of like a puzzle. And so today we're going to be using Oreo cookies to model that. So if you're watching this at home, maybe ask an adult or a grown-up at home for some help, and you're going to need to go get these supplies. You're going to need some Oreos. I have 4 here, but ask your grown-up how many you can have for this modeling experiment. I also have a paper plate to put them on, and I have a marker. You can use a pen or a pencil. You just need some type of writing utensil so that you can remember the different types of boundaries we'll be talking about today. So after you've gathered your supplies, which if you need to, go ahead and pause this video so that you can go get your supplies and then come back. Once you've got your materials, we are going to start setting up our plate. So I'm going to put my cookies to the side for a second. And I've got my plate here. And the first thing I'm going to do is draw a big T so that then I have 4 parts of my plate. So I'm going to draw a line straight up and down the middle. And then I'm going to turn it and I'm going to do the same thing. So now I have 4 sections of my paper plate. It doesn't have to be completely even. You just want to divide it into 4 different sections. The next thing we're going to do is label those sections so that when we model with our Oreo cookies, we can remember what we're modeling, because that's super important part of the experiment to not only have fun, but also to learn about the different types of plate tectonics. So the first one we are going to talk about is transform. So you can either write a T for transform, or you can write out the word transform. So I've got one section labeled here. The next one we're going to talk about is divergent. So I'm going to write the word divergent on my next section. The next one is convergent. 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 And then the last one we're going to talk about is subduction. Subduction. So at this point, your paper plate should have all 4 types of boundaries labeled so that we can get started with the Oreo cookies. If you need to, go ahead and pause this video so that you can write down the 4 different types of boundaries before you move on to the cookies. Okay, so now our next step is to start taking our Oreo cookies apart. So I have found the best way to do that is take an Oreo cookie and twist the 2 cookies opposite directions. So I'm going to twist them like, ooh, this one's kind of tough. There we go. So now I have one side with cookie only and one side that has cookie and cream. Okay. The reason we're doing this is because the cookie side is like the crust of our Earth, the outside where we live, this thin layer. This half of the cookie with the cream on it is the mantle. This is the liquid molten rock that the crust is floating on. So you can kind of see this with your cookie. If you take your cookie half and you put it back on your cream, you can kind of slide it around. Oops, there we go. Awesome. So that's how a plate tectonic floats and moves around on the mantle. Okay, so let's go ahead and separate all of our Oreos that we're using today for this experiment. Okay, so I've got all of my cookies separated. We're ready for the next step. So the next thing we're going to do is we have to create plates. So right now we just have one big plate, but we know that the Earth has many smaller tectonic plates. So to model all of these different boundaries that happen, we're going to break our cookie, just the cookie side, into two parts as best we can. Sometimes they'll be a little bit off. It won't be exactly half, and that's okay. Sometimes you'll get 3, maybe 4 pieces. No worries, just do your best. Okay, so go ahead and break all of your crust parts, your cookies only, into 2 pieces. Go ahead and pause the video if you need to do that. Okay, so now we're going to start modeling our different boundaries for different tectonic plates. So you're going to take your first cookie. This is from my transform section. So I picked it up off of my plate from where it said transform. Now, the first thing we're going to talk about transform boundaries is that they slide past one another. And I know it's kind of hard to see on these pictures, but these 2 arrows are going opposite directions. So they're sliding past each other. And you can see on the Oreo cookie how our 2 tectonic plate cookies are sliding past each other. Now, what happens when this happens on Earth is we get a lot of earthquakes. And so maybe you've heard about earthquakes happening in other parts of the world, and they can be very dangerous because the Earth is shifting underneath us. So that's a transform boundary. So when you're done modeling your transform boundary, go ahead and put it back on your plate and kind of leave it so that you can see that your 2 plates are moving past each other. The next boundary we're going to talk about is the divergent boundary. So a divergent boundary is where your 2 cookies or your 2 tectonic plates are moving away from each other. They're going apart. When that happens, as you can see with our cookie, we can see that cream filling in the middle. And so that means that the molten lava, the magma that's under the surface is coming up in that gap. And that's how we get new crust and new rock. So when that happens on the Earth, we have rift valleys that form, and we have mid-ocean ridges. So these are basically new sections of the Earth's crust. So when you're done with your divergent boundary, you can put it back on your plate where it says divergent and have it open so you can remember that divergent moves apart. For our next boundary, we're going to look at convergent boundaries. So convergent boundaries are where 2 tectonic plates are coming together and they're actually crashing into each other. So one thing that can happen with that, you can see with the Oreo cookies, when you press them together, they might start to come up. And that, when it happens on Earth, creates mountains. It's one way that mountains are formed. So once you've modeled your convergent boundary, you can go ahead and put that Oreo cookie back on your plate where it says convergent. And the last type of tectonic plate boundary we're going to talk about today is subduction. This is where two plates are coming together still, just like with convergent boundaries, but one plate is going under the other plate. This happens a lot when you have lands on one side of your tectonic plate, or one tectonic plate is land, and the other tectonic plate is ocean. The ocean is heavier, more dense, so it actually goes under the land tectonic plate. And that is where you can get volcanoes, because the magma is being pushed out and up through the crust on the land. So as you can see with our Oreo cookie next to me, the Oreo cookie kind of crumbled as we pushed it under into that subduction zone, where the ocean plate went under the land plate. Wow. Great job modeling your Oreo cookies with these different tectonic plate boundaries. Go ahead and put that subduction cookie back onto your plate where it says subduction. So now you should have on your plate 4 different models of the tectonic plate boundaries. And each cookie should look a little bit different to represent how these different tectonic plates come together, pull apart, or slide past each other. So that is our Oreo cookie modeling for today. Each Oreo cookie was a different type of tectonic plate boundary. And the tectonic plates are super important because they're a crucial piece of the rock cycle. That's how we get new rocks and recycle old rocks. It takes a very, very long time for the rock cycle to happen most of the time. And tectonic plates don't move very fast. So most of the time, it doesn't happen as fast as we saw it with the Oreo cookies. It takes billions. It takes a long, long time. So today, we learned about some of the things that geologists do. We talked about the rock cycle and the 3 different types of rocks. So we talked about sedimentary, metamorphic, and igneous rocks with Christina. We also talked about some of the properties and characteristics of them. Then we talked about the different types of tectonic plate boundaries with me, and we modeled it using Oreo cookies. So we talked about the transform boundary, divergent boundary, convergent boundary, and subduction boundary. Wow, we talked about a lot today, but if you want to learn more, go to our geology learning unit on our website at brooklynbridgepark.org. I'm so glad you joined us today to have some fun, to learn more about rocks, bundle some tectonic plates with Oreos, and hopefully enjoy those Oreos at home when you're done. Thank you so much for watching, and we hope to see you next time. Bye, everybody.